Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 5 of module 3. In this module, we are studying electrical and magnetic properties of atoms and molecules. Now friends, let us continue with the previous few more aspects of the dipole moment measurements. We will see one or two more numericals herein. So friends, let us continue with one more numerical of previous type. In previous numerical, we have seen the dipole moment of CH3Cl molecule. Now herein, let us have a look at the dipole moment of CH2Cl2 molecule. Now in this molecule particularly, it is given that the dipole moment of carbon chlorine bond is 1.47 dB with chlorine as negative end, and the other thing, dipole moment, that is dipole moment of carbon hydrogen bond, is 0.4 dB with carbon as the negative end. Okay, now in this particular molecule, you can see we consider that the atom CLA and CLB. So chlorine atom A type, and first atom of chlorine and second atom of chlorine, that is CLA and CLB, they are to lie on the plane A. So both of them, they are lying on this particular plane A. You can see this plane A, and the atom HA and HB, they are on plane B. So this is my plane B. Okay, now we resolve each of the two bond moments in a plane along the two mutually perpendicular axes, of which the x-axis is common. Now this x-axis is common to both the planes, this plane as well as this plane. So A plane and B plane. So my A plane contains both the chlorine atom, my B plane contain both the hydrogen atoms. Okay, so now the component along x-axis is dipole moment along x-axis component will be simply this negative of dipole moment of carbon chlorine A atom minus dipole moment of carbon chlorine B atom minus dipole moment of carbon hydrogen A atom and minus dipole moment of carbon hydrogen B atom into cos of theta by 2, that is 54.74 degrees. So if I substitute these values, I get the dipole moment along x component as minus 2.16 d. Now I'll calculate the dipole moment along YA and dipole moment along YB. So let us have the dipole moment along YA. So mu of YA will be equal to mu of carbon chlorine A atom minus mu of carbon chlorine B atom, because it is along YA direction, sine of 54.74 degrees. Okay, and that is equal to 0. Both of them, they are same. And then let us have the dipole moment along YB direction. So along YB again, if you see the mu of YB, that is dipole moment of carbon hydrogen of A atom and dipole moment of carbon B hydrogen atom. So this is again same, they will cancel out each other, and therefore dipole moment of YB is equal to 0, and therefore the dipole moment of CH2Cl2 will be the only which is responsible only along x-axis. The dipole moment along x-axis will be only remaining from all the three components, and therefore the dipole moment of CH2Cl2 will be 2.16 dB. Okay, similarly, now I can estimate the dipole moment of CHCl3. Okay, so here in this case, it is given that dipole moment of carbon chlorine atom carbon chlorine bond is 1.47 dBA with chlorine as negative end, and then dipole moment of carbon hydrogen atom, carbon hydrogen bond is equal to 0.4 dBA with carbon as negative end. So in this case, now if I consider, look at this figure, what is happening in this case? Now there are three chlorine atom: chlorine A, chlorine B, and chlorine C. So my chlorine A and chlorine B, they are lying on plane A. Okay. And now my chlorine C atom and hydrogen atom, they are lying on plane B. Now herein, once again, we resolve each of the two bond moment in a plane along the two mutually perpendicular axes, and out of which that this x axis is common to both the planes. Now again, if you look at this particular geometry, I want to find out the, I will first find out the dipole moment along x component. So dipole moment along x component will be minus of dipole moment of carbon chlorine A atom minus dipole moment of carbon chlorine B atom. So plus the dipole moment of carbon chlorine C atom and minus dipole moment of carbon hydrogen atom. So look at the direction of carbon chlorine atom, isn't it? So this will be in this particular direction, because now it has got chlorine atom is at negative, and that, and therefore this direction will be on in this direction. Okay. So this particular dipole moment is this particular bracket multiplied by cos of 54.74 degrees. So if I calculate this dipole moment along x component is nothing but the dipole moment, negative of dipole moment of carbon chlorine A atom minus dipole moment of carbon hydrogen atom. Okay, so the bond between carbon and chlorine A atom, this, and dipole moment along this carbon hydrogen bond. So these two bonds will only be responsible for the dipole moment multiplied by cos of 54.74 degrees. If I substitute all the values, I get the value of dipole moment along x component in this case will be equal to minus 1.08 dB. Now I have to calculate it along YA component of axis and YB component of axis. So along YA component of axis, the dipole moment along YA component will be the dipole moment of carbon chlorine A bond minus carbon chlorine B atom into sine of 54.74. Since both of them, they are same, equivalent, so the whole dipole moment will be 0 along YA component of axis, and along YB component of axis, now I have the minus of dipole moment of carbon chlorine C bond and minus dipole moment of carbon hydrogen bond sine of 54.74. So if I substitute the value of this dipole moment of carbon chlorine C atom is minus 1.47 dB minus 0.40 dB, which is the dipole moment of carbon hydrogen bond, and my sine of 54.74 degrees. So the value of dipole moment along YB component of axis will be minus 1.53 dB. So the overall dipole moment of CHCl3 will be this dipole moment mu is equal to square root of mu x square plus mu ya square plus mu yb square. If I substitute the values, I get the dipole moment of this molecule CHCl3 is equal to 1.87 dB. Okay, so this way I can calculate the dipole moment of these molecules based on its geometry. Okay, group moment. This is one of the important slide. Earlier also we have seen in one table the group moments. However, in this particular case, let us see the calculation of group moment, how, on what basis we calculate this group moment. Now, in evaluating the dipole moment of say benzene derivative, the study of group moment basically is of great importance basically. Now, because group moment is going to give me a broader idea about the positions of the substitution rather than the concept of bond moment. Say, for example, if I consider the example of say chlorobenzene. Now, in chlorobenzene, if I assume that all the carbon hydrogen bond linkages in benzene, they have zero bond moments. Now then, in such case, the observed dipole moment of, say, it will have the observed dipole moment, say, of 1.55 dB, which is applicable to chlorobenzene, and which may be assumed to arise from basically the carbon chlorine linkages. Okay, and therefore the group moment of chlorine atom is actually minus 1.55 dB. Correct? So the sign of the group moment indicates the direction in which the group moment it is acting. So positive sign implies that the group moment acts away from the benzene ring, whereas the negative sign implies that it acts towards the ring, isn't it? We have tabulated some of the value in this particular table. Now this table includes the group moments of few groups. So nitrate group, cyanide, hydroxide, then chlorine, hydrogen, methyl group, amines group. So we have included this particular group moments. So for nitrate group, it is minus 3.98, cyanide it is minus 3.8, hydroxide it is minus 1.6, chlorides it is minus 1.58, hydrogen, for hydrogen it is 0, for methyl group it is plus 0.4, for amines it is minus 1.53. That means, as I said, the positive sign implies that the group moment acts away from the benzene ring, which is applicable in this case of methyl group, whereas the negative sign implies that it acts towards the ring. That means in all the other cases, like nitrate, cyanide, hydroxides, chlorides, amines, in which they will act towards the ring, isn't it? Now this table particularly include the group moments of particularly these groups. We can have a long table which we have seen earlier in one of the previous lectures, wherein we try to include many other group moment of many other groups. So the dipole moment of any substituted benzene, it can be derived from these expressions which are mentioned over here, which we have already seen earlier. So we can derive the group moment or dipole moment of any substituted benzene from the addition of the group moments because this particular is the additive property. You can consider, for example, here the arrangement of two bonds. So if I consider two bonds, for first bond, the let us say the dipole moment is mu1, and for other bond, dipole moment is mu2, and both the dipole moments or the bonds, they are inclined at an angle of theta, and this angle is basically between the two bonds. Okay, so now the addition of these two dipole moments may be carried out by adding separately the two x and y components of dipole moment of first bond and dipole moment of second bond. Now this is so done that so as to give the dipole moment along x component and dipole moment of y component respectively. And then by employing the expression of this kind, we get the resultant moment of the two moments. Okay, so if I have uh, theta 1 and theta 2, these are the two angles for, say, dipole moment of first bond and dipole moment of second bond with x axis. So we have the along x component of dipole moment, we will be having this kind of expression. So mu1 x plus mu2 x is equal to mu1 cos theta 1 plus mu2 cos theta 2. Similarly, dipole moment along y component will be mu1 y plus mu2 y, that is equal to mu1 sin theta 1 plus mu2 sin theta 2. Correct? So accordingly, these two components of dipole moment, they can be calculated. And therefore, if I want to find out the resultant dipole moment, I can substitute these values in this particular expression. So it will give me square root of mu1 cos theta 1 plus mu2 cos theta 2 square plus mu1 cos sin theta 1 plus mu2 sin theta 2 square to the power half. So if I solve this, so I get this particular expression, and this can be simplified in this form. That is, my resultant dipole moment will be given by mu1 square plus mu2 square plus 2 mu1 mu2 cos theta to the power half. Now, based on this particular calculation of dipole moment from the group moment, we have utilized this concept in solving many of the numericals or many of the examples wherein we can calculate the resultant dipole moment based on it. Especially this example is applicable to substituted benzene kind of example. You can say disubstituted benzene or chlorobenzene monosubstituted benzene. I can take this example and I can find out the dipole moment value using such kind of formulas. So now let us look at some of the numericals. In this particular numerical, what we need to prove. Herein, we need to show that the dipole moment of 1,2 disubstituted benzene and 1,3 disubstituted benzene are 1.732 mu and mu respectively. Now, this mu basically is the dipole moment of monosubstituted benzene. Okay. So now how to prove this? It is very simple. What we will do, just now we have seen the resultant dipole moment calculation formula for particularly substituted benzenes. Okay. So for 1,2 disubstituted benzene, the angle theta between two vectors is always 60 degrees. So if I substitute this value into this resultant dipole moment formula, that is mu total is equal to mu1 square plus mu2 square plus 2 mu1 mu2 cos theta to the power half. So I can substitute this value and I can get the result. So total dipole moment will be square root of 3 mu, that is nothing but 1.732 mu, correct? So therefore we have proved that the dipole moment for 1,2 disubstituted benzene is 1.732 mu, whereas for 1,3 disubstituted benzene, the angle theta between two vectors is 120 degrees. And therefore, if I substitute this value into the formula, I get the value that total resultant dipole moment is nothing but mu. And therefore we can very easily prove that the value of dipole moment of substituted benzene can be the given value. Okay. Let us now have a look at the another numerical. So what is asked here? Herein it is asked that the dipole moment of chlorobenzene is given as 1.70 dBi. Now we need to calculate the corresponding value of 1,2 and 1,3 dichloro substituted benzenes. Also, after obtaining these values, we need to compare these results with the experimental value which are given for 1,2 dichlorobenzene. So dichloro substituted benzene, it is 2.53 dBi, and for 1,3 dichloro substituted benzene, it is 1.68 dBi. Okay, so we need to first calculate the corresponding value of dipole moment for 1,2 dichloro substituted benzene and 1,3 dichloro substituted benzene, and then we need to comment on these values with respect to our calculated values. So now we know that these values are given for 1,2 disubstituted benzene is 1.732 mu, and for 1,3 disubstituted benzene it is mu respectively. So I know what is mu. Mu is given as dipole moment of chlorobenzene is given as 1.70 dB. So my dipole moment of 1,2 disubstituted benzene will be 1.732. So mu is nothing but 1.70 d. So 1.732 multiplied by 1.70 dB is equal to 2.94 dB. Okay. And for 1,3 disubstituted benzene, since it is mu, so substitute the value of mu, that is 1.70 dB. So now both the values we have. However, what is given? What is given? For 1,2 disubstituted benzene, the value is given as 2.53 dB, and we have got 2.94 dB. Whereas for 1,3 disubstituted benzene, the calculated value is 1.70 dB, and the given value is 1.68 dB. So naturally, if we compare these results with the experimental results, we actually find that the agreement is in great this particular results is in great agreement for 1,3 dichlorobenzene. That is 1.70 dB is very close to 1.68 dB. So it is in excellent agreement. However, for 1,2-dichlorobenzene, this agreement is not satisfactory, because what we get is 2.94 dB, and what is experimental value? It is 2.53 dB. So there is a difference. Basically, this may be due to either or both of the following reasons which are mentioned over here. Now, what are these reasons? The reasons are the angle between carbon chlorine bond vectors may be larger than 60 degrees sometimes, which is because of the mutual repulsion of the relatively negative chlorine atom. That may be the one reason. And the other reason is the magnitude of bond moments may be modified by their proximity. So this can be the other reason for not matching the experimental and calculated values in case of dipole moment of 1,2-dichloro substituted benzene. This is one of the very important numerical which we can see. Now, in this particular numerical, what we need to do is the dipole moments of nitrobenzene, toluene, and chlorobenzene. They are given as 3.93 dB, 0.46 dB, and 1.55 dB respectively. And now we need to calculate the dipole moments of the following compounds. So number one is ortho meta para dinitrobenzenes. Number two, ortho meta para dimethylbenzenes. Third is ortho meta para dichlorobenzenes. Fourth is ortho meta para nitrotoluenes. Fifth is ortho meta para chlorotoluenes. And sixth is 1, 3, and 1, 4 chloronitrobenzenes. Very interesting numerical this is. We will see one by one or step by step in all the cases how to calculate. Okay, so now let us first start with the ortho meta para dinitrobenzenes. So now we know basically that for ortho position and meta position, the value of dipole moments are given as 1.732 mu or square root of 3 mu and mu respectively. Okay, so this is what is available with us. So what we have now, ortho meta or para dinitrobenzenes. In that case, the ortho dinitrobenzene case is where mu is equal to, I can substitute this value. I can substitute this value like 1.732, which is known to me, multiplied by mu. What is mu? Which is given over here. So it is 3.93 dB. So it is nothing but, in case of ortho dinitrobenzene, it is 6.81 dB. Similarly, in case of meta-dinitrobenzene, the value is simply mu, which is nothing but 3.93 dB. And in case of para-dinitrobenzene, since the angle is of 180 degrees, my dipole moment will be equal to 0. That is as simple as it is. Okay. In second case, that is ortho meta para dimethylbenzenes. Again, in this case, so ortho dimethylbenzene case is mu is equal to 1.732 into 0.46, which is given over here, 0.46 dB. So the value is 0.797 dB. Meta dimethylbenzene, it is 0.46 dB, and para dimethylbenzene it is 0. So dipole moment is 0 in case of para dimethylbenzene, because the angle is 180 degrees and the dipole moment, individual dipole moment, they cancel out each other. Similarly, third case is ortho meta para dichlorobenzene. So now in case of ortho dichlorobenzene, again my dipole moment is 1.732 into 1.55 dB, which is nothing but 2.68 dB. Now meta dichlorobenzenes, in this case it is mu is equal to 1.55 dB, because it is given, actually the value in such case is 1,3 disubstituted substituted benzenes kind of thing it is, and therefore the dipole moment is 1.55 dB. And para dichlorobenzene, since the angle is 180, my dipole moment is 0 in this case. So next case is ortho meta para nitrotoluenes. Let us have look at it. So now the fourth case is that way interesting. So we need to calculate in case of ortho meta para nitrotoluene. Okay. So now what do we have? We have the dipole moment of nitrate group, that is minus 3.93 dB, and dipole moment of methyl group, that is 0.46 dB. And the ortho nitrotoluene, it has an angle of 60 degree, isn't it? the position of nitro group is. So in case of orthonitrotoluene, we have got the two angles between two bond moments, that is two bonds is 60 degrees, and therefore I can use this formula. The dipole moment per dBi will be equal to mu1 square plus mu2 square plus 2 mu1 mu2 cos theta to the power half. So if I substitute these values, mu1 square minus of 3.93 square plus mu2 square, that is 0.46 square, plus 2 into mu1 into mu2 into cos of theta, that is half, because angle is 60, and to the power 1 by 2 if I calculate. So for orthonitrotoluene, my dipole moment is 3.72 dBi. Okay. Similarly, if I take the case of metanitrotoluene, it will, the angle between two bond moments will be two bonds will be 120 degrees, and therefore if I substitute these values, that is dipole moment per dB will be, in such case, if I substitute mu1 square plus mu2 square plus twice mu1 mu2 into cos of 120, so this will be, if I calculate, I get the overall dipole moment of metanitrotoluene will be 4.18 dBi. Now in case of paranitrotoluene, the angle is 180 degree, that is exactly linear. Two groups will be oppositely placed, and therefore, so now dipole moment per dB will be mu1 square plus mu2 square plus twice mu1 mu2 into cos of theta, that is 180. So if I substitute this value, I get the dipole moment will be equal to 4.39 dB in this case. Alternatively, what we can how we can find out the paranitrotoluene in such case, we have the dipole moment can be derived directly by the simple algebraic addition of the two dipole moments, uh, as the two vectors points, they are in the same direction, and therefore the total dipole moment in such case will be the dipole moment of nitrate group plus methyl group. So it will be 3.93 plus 0.46 d, that will be 4.39 dBi. So this way we can calculate. We can now solve for say fifth example, which is orthometra para chlorotoluenes. In such case, you can see here the ortho meta para chlorotoluenes. What we have now, see dipole moment of chlorides, it is minus 1.55 d, and for methyl it is 0.46 dBi. So now orthochlorotoluene, the angle is now 60 degrees. So if I substitute these values, so I get for orthochlorotoluene, my dipole moment will be, after solving this, I get 1.379 dBi. Similarly, if I solve it for metachlorotoluene, angle is 120 degrees. I know mu1, I know mu2. So mu1 square plus mu2 square plus twice mu1 mu2 cos theta, that is 120 degrees. If I substitute, I get the dipole moment is equal to 1.824 dBi. And for parachlorotoluene, the angle is 180 degrees, and therefore I get the dipole moment is equal to 2.01 dBi. Or I can add these two vectors and I get the dipole moment as 0.46 dBi plus 1.55 dBi, that is equal to 2.01 dBi. Okay. Similarly, the sixth one is 1,3 and 1,4 chloro nitrobenzenes. So in such case, what we have, again dipole moment for chlorides, it is minus 1.55 d, and now for nitrates it is minus 3.93 dBi. So for 1,3 chloronitrobenzene, the angle will be 120 degrees. Okay, and therefore if I substitute this value in the formula of dipole moment, that is mu1 square plus mu2 square plus twice mu1 mu2 cos of theta to the power half, it will be, I will get the dipole moment for 1,3 chloronitrobenzenes will be 3.43 dBi. And similarly for 1,4 chloronitrobenzenes, the two vectors points in the opposite direction, and therefore the magnitude of dipole moment will be the 3.39 dBi minus 1.55 dBi, which is equal to 2.38 dBi. So this is how I can utilize this bond or group moment calculation, or the particularly the cases of substituted benzene kind of structure. I can find out the dipole moments using this kind of formula, especially that mu is equal to mu1 square plus mu2 square plus twice mu1 mu2 cos theta. This formula is particularly useful for this kind of disubstituted or substituted benzenes kind of examples. So friends, in this lecture and in previous few lectures, we have seen the applications of dipole moment and its utility of the measurement of dipole moments. And particularly, we have also seen how this particular dipole moment, it can be utilized in calculation of ionic character. It can be utilized in calculation or finding out the shape of the molecule. We can find out the cis and trans forms of the isomers. We can also find out the dipole moments in case of the disubstituted or substituted benzenes kind of example. So we have explored the some of the interesting aspects of the dipole moment measurement. So friends, particularly we will stop here in this lecture for the dipole moment or the electrical properties of the atom and molecules. From particularly next lecture, we will start with the magnetic properties of the atoms and molecules. So thank you friends.